Okay, so we covered the first three, and the lecture 3 is the most important one, which is we're going to carry on. Last Friday I was planning to assign you a homework. I did not, so this Friday I will. Okay, and let's start System Dynamics 1. So in System Dynamics 1, they're talking about how we're going to use this change of rate thing into calculations, right? The best example is giving you here, which is a useful application which using a dq by dt. So again, if I recall what is dq by dt, this is actually anything out there when it changes. Like you can graph it like this over time with the quantity. So the quantity over time, right? When the time flies or the time moves, right? The quantity there, something happened to the quantity, right? So that means something happened to these values as well. So this is reality for everything. So if you have a time something, and there's no such a thing which is a b constant over the time, right? Something like constant. You feel like anything is constant, but it is not really constant. Even the piece of metal never be a constant. If you really go close and look, the atoms of the structure, whatever the structure you have with the metal, this also have changes in every minute it does. Okay, that's why it's getting corroded. It's a long time when it's stay there, and it's get damages. It's get especially it's getting cold at night. Hot at the daytime, the structure changes. Okay, so nothing is permanent in this world. So that's what it means. Nothing is permanent. Even you growing, right? So is everything. So in that case, so we decide how to calculate things, which is we just get small change, which is delta Q in this case, right? It in given small time, which is delta T, right? Again, you can define this as dq over dt, which is changing something, right? What is this slide is talking about is a carbon-14, radioactive carbon. This is something that you have in your bones, right? In your bones, you have something called carbon-14. Once you die, this start decaying. But the rate of decaying is very, very low. Because of that, even for today, you will see a piece of this bone exist, right? Piece of this will exist. So in that case, you can see initially how much it was there, assuming that saying how much it's decayed. So amount of decaying, and if you know the change of rate per year, then you can calculate how many years it took. And we went through this, and I explained that last time. So I'm just recalling the idea of this. What is this dq by dt means? So that's what I'm just pulling out again, right? And so I hope you have a clear idea what is this dq by dt means. Okay. Right. So saying that, so that is a differential equation. I think I covered this last Wednesday before the quiz. Even we did not test you in this on the quiz. So this is the definition of it. So you go through the book, you can understand that. And we talk about Malthusian model, which is, you say the change in population over time is directly proportional to the initial population. So what this means is, of course, if I have directly proportional, if you want to change it to equation, so what you do is you apply some rate of change, right? Okay, so now we want to analyze this. What is this math statement means? This means, right, two things. One is if it is a really small change on your population, over really small time, right? Really small population change over really small time, that is also equivalent to the rate of whatever is changes multiplied by whatever the existing population, right? So it's always depending on the existing population. We call this initial population, right? And you multiply the initial population with some rate, some kind of a change rate. That is another way of illustrating dp by dt, which means little change of population or a little change of time also equivalent to the change rate multiplied by the initial value, right? So if you understand this part, it's much more easy for you. Don't get complicated by the symbols. What is this says is there's a little change on anything uh, over the time is equivalent to the rate of change. This is actually a value somebody has to give. How do I find this value? Well, if you have a lot of data set, uh, table of data, and then you can see the change, right? Right now, if I have 2, next time when you're looking at, you can see 4, and next time when you're looking at it, you can see 8. And that means it's, the change is something multiplied by this give you 4. It's actually 2. If you multiply some initial value by 2, it gave me this. So if this is the rate, you can assume the rate. Okay, so now if I multiply these two, give you this value. So eventually, the rate multiplied by the original value always give you a new value, right? So in that case, I can assume, okay, this is the rate. So in this case, the rate is 2. If that happens, right? Next time, 16, 32. So that means the initial value always multiplied by 2 give you another value, right? Okay. So this is one way of looking at it, right? So this is how you calculate the rate of changing anything. So if you have a big data set, and if you can find a correlation between these values, right? When you're looking at these series of these values, you can see it's each time is doubling. So that means it's multiplying by 2 each time. So in that case, I know the rate is 2, right? So this is what the rate is. So in this case, yeah, we can do something like that and see what is the relationship between the rate and the population. So this one you can actually calculate by many data collection of the data, right? This is something you do for your project actually. You come up with the equation like this by looking at what are the correlations between the values you get, okay? So when you get the values like this, you can initially find out what's going on, right? And by that, you know what is this rate of change means, or the growth, right? So this is something that we did last lectures on calculus, and we talk about this, and we talk about why we writing it like this form, right? And then what is the purpose of it, right? That is, the purpose is calculating instantaneous values, right? Yeah. And to calculate the instantaneous values, what you do is you divide it to small intervals and then having this equation, right? So if you don't have that equation, yeah, of course, if I collect the data and see the relation also, we can find the value. So that's all. So I don't want to talk too much and confuse you, but this is what it is, right? So so change of rate, rate of change population, and the growth rate R has no, uh, uh, those are two different things, right? This is the growth rate, right? Or the rate, that is the changing rate of the value. And this is actually the instantaneous rate of change, okay? So these are two different values. Don't get confused with these terms, right? Okay? These are so many terms. So we call it growth rate is the R part. Okay? This one, which is called rate of change of the population. This one and this one is two different things. This guy has three names: growth rate, instantaneous growth, you can call it, yeah, and the continuous growth, you can call that. Okay? But rate of change of the population is the one which is called dp by dt. Right? So what you should learn here, the terminology, right, and the meaning of it. This right here and this right here. So keep that in mind. If you are not familiar with it, this is very hard to absorb, but well, that's what it is. So you should be able to understand. And the proportionality always means there's a constant multiplication. So that is what the proportionality means, right? Is that clear? Are there any things that you want me to address here? Did you get it? Is there anybody you want me to repeat this? No, all good? Right, so I hope you get that. Right, so this is an example of it. So this is a bacterial population. You say initially there are 100 of them. And instantaneous growth rate, which means the R value, is 10%. So it says, well, 0.0. If it is 100, you have 10 of them growing. So that's what it means, right? Right, so before I carry on from here, what does this means actually? Percentage. What does this means? Can anybody explain to me what this percentage means?
Every hour it grows 10%.
Well, yeah, in this case, I'm just asking what is the percent means? Forget about this problem here. Tell me what is the percentage means? Why you need a percentage to calculate things? Anyone? So you say 5% discount. What does that mean? Or yeah, 20% growth. What does this mean? What does this percent means?
Part of a whole.
The existing amount or the starting amount?
Well, it is actually saying if you take 100 as the total, how much effect it has. Okay, this is what it means. Like, for example, let's say you have 1,000 people. Okay, and out of 1,000 people, 200 of them are wearing hats. Let's say they have hats. 200 of them has hats, right? So out of 1,000 people, 200 of them have hats. So how do I show this as a percentage? How do I convert this to a percentage? Well, this is how you do it, right? This is, you get the meaning of percentage by this. If you have 1,000 people, you say if they are 100, if they are 1,000, then amount of people having hats is 200. Okay. Then you say if there is one person, then how many are having hats? How do I convert this to one? How do I convert 1,000 to one?
Divide by 1,000.
Divide by 1,000. So if I divide this side by 1,000, I have to divide this by 1,000 too. So that is how the equation stays balanced. So in that case, I had to divide this by 1,000. Right. So when the percentage comes, it's always calculate the total amount. This is the total amount. You assume, okay, this is 1,000. It can be 2,000 some other time. It can be 3,000 on some other time. So in that case, I had to give each time how many hats are there, right? Instead of saying like this, for the total changing total each time, I would say I get a standard total, which is 100. So always I'm calculating for 100. So in that case, it's easy for me to tell, right? This total always changes. It can be any value. And instead of I'm giving a different number of hats for each value, right? 250 maybe, 350 maybe. So each time if I say total number and then 350. So that is too much work to do. Each time you come and say out of 2000 I have 250. Out of 3000 I have 350. So like that. So whatever the value here, you have to give the total value and the result, right? So this is the result actually, right? So that is too much work. So because of that, there's a standard, a universal standard. You say everything for a total of 100, what happens? So how do I convert 1 to 100? So if I want to say 100, then. So how do I change this 1 to 100?
Multiply by 100.
Multiply by 100. So if you multiply this side by 100, you have to multiply the other side by 100 too, right? So that's how you get the percentage. So in this case, if I have 1,000 people and then I have 200 hats, so that means, let me cancel out 2 zeros to 2 zeros, 1 0 to 1 0, right? So this is what? 20% of the total population have hats. That's what it means, right? So this is how we're showing it, right? This is how we're making it, okay? So if you have any issues on that, what is the percentage and what is this, the people talking about percentage, right? So that's the best way to illustrate that. So that means always, if there's a varying total number, the varying or total number means it can be changed anytime. So instead of you telling, okay, 1,000 for 1,000, I have 2,200 hats. For 2,000, I have some other value. 3,000, I have some other value. So you have to give two values in that case. Instead of saying that, if I say 20%, so that means it is out of 100 this many. So I can convert it every time, anytime I want. So again, if I want to convert this back to the total number, instead of 1,000, if I want to calculate for 1,000, what I do is simply I write like this. This is what it is, multiply by 1,000. So eventually you get 200 back, right? You get 200 back. So if I want to calculate it for 3,000, simply I write like this and multiply by 3,000 total. Then you get how many hats you have. So simply this many, right? So that is 600 of them have hats. So like that, that is what percentage means, okay? So if you never know what is percentage means the total number, you convert it to 100 and calculate the result, right? This is for the discounts in the shops or whatever you do. You just say, okay, if it is 100, then this is amount. Then you can calculate, convert that to any amount. So if it is $2,000 value something, then simply you multiply that and divide by 100, you get the answer, right? Okay. So that is what the percentage means. So we talk about a lot of percentages in these chapters. So that's why I just want to point out what does it mean. So right, 10% means, okay, 10 divided by 100, right? You multiply that by any number, the total number, that gives you the answer. In this case, total number is the population, and you multiply by 10%, right? If it is 100, yes, that's what it says. Okay, is that clear? Yeah. Okay, so if it is clear, it's good. Okay, so now in this example, it says here the growth rate, the rate is 10%. That means rate is given out of 100 value. So if you want to convert that to the total amount, what you do is you multiply this by the total amount, which means P in this case. So, so initial condition in this case is P equals 0. 100 in that case, obviously, the change in population is equal to what? If you calculate this, what is the answer you get is I have dp over dt. That is a little change. Our digital time is equivalent to the rate that I have given is this much, multiplied by the initial value, which is 100, right? So on another way of writing this is it's 10%. So when you're writing this form again, it's 10 over 100. So this is what the 10% means. And then you multiply that by 100, you get this. So this means what? The change in little time is this, right? So the change in little time is 10. So what does that mean? The total value is what? What is the total value? So this is measured in hours. So what is the next hour total value is going to be?
1,000.
Not really, no. This will give you, after hour, you have 10 more than the initial value. So what is that? So this means a change, right? This is a change amount over time.
110.
110, yes. So you have the initially 100 people. Initially 100 you have, all right? And now after, if this one reach 1 hour, I get 10 of them. So that's what it means, right? So then I have change of value is 10. So this is equal to 110 total. What does this mean? This means the old value plus the change give you the new value, right? Yeah. Old value is initial value, and the change is this value, give you the new value. Okay. So this is the idea here. This is what you're calculating by this. So this one right here is this equation. Calculate nothing but the change. So if you calculate it in hours, it's already say it's hours, so the delta t is 1 in that case, right? Change in time is 1 because I'm calculating in each hour, right? And then I'm asking what is this p value, right? Okay. So do you want me to explain this anymore? All right. Guess you get it, right? Right, so this is the finite difference equation. So the difference means old value plus the change give you the new value, or I can say new value, old value, new value minus old value equals change value. So that is the difference, right? The finite difference equation is simply saying the new value is equal to old value plus the change in value, right? In math, you can write this as P equals P0 plus delta value, which is change, delta P for the population. So this is a change in population plus the initial population is equal to the current population. You can say current population is equal to initial population plus change in population, right? So this is, keep this in mind. It has a heavy big name here, but simply what he's saying is the current value is equal to the old value plus the change, right? Okay. So as simple as that, but it's give a big name. So if you're not familiar with the name and things like that, this is the time to absorb that and understand, right? So far, so good, yeah? So very simple things I teach you so far, but it look like heavy math, but it is not. Just this is what I'm explaining, okay? Right. So this is one question and example here. For simulation with a dynamic tool or a program, we write the considered time advance in small increments. The small increments is delta t. steps for time t, and the length of time step is delta t, right? So that means very small, like a half a second, things like that, right? So the previous time means what? If the current time is 2 o'clock, the previous time is, let's say, let's do an example here. Instead of this example, I will get something familiar for you. Well, I always pick 2 o'clock. I don't know why. If the current time is 2 o'clock, and the time period, I'm talking about 5 minutes. 5 minutes. 5 minutes. And so what does this mean? What is the previous time in that case? Previous time. What is previous time?
1:55.
1:55. So how do you calculate that? Well, current time, which is 2 o'clock, minus 5 minutes, right? Yeah, that give you 1:55. So that is what this means. The time minus delta t is the previous time. Okay, in literary, that's what it is. Right. So, well, here it says, okay, so you have 7.75 seconds, and delta t is 0.25 seconds, and the previous time is obviously 7.75 minus 0.25 gives you 7.5 seconds. 0, you don't have to worry about, okay? That's just a simple calculation. Right, so that is another baby step. You have done this tons of times when you're in the high school and come here. Right, so here it is getting a little complicated, but it is still, we talking about the new population equal. All population plus the change. Now where I'm heading from this, I'm going to trying to show you the connections between and how you're really going to play around with this delta Q or a P over dt. What is the connection between this and the rates and then the initial and the previous populations, right? I mean the new populations and the previous populations, new, previous, right? Populations, the rate, and these values. What are the connections? How can I play around with these things? So that's what we're going to learn in this area right here. And then later on, we're going to talk about something else. But I want to point out here, only focus on these things: previous population, current population, and the growth rate and things like that. Okay. Right. So let me address that and make sure you understand it. So pay attention. So if you have a monkey mind thinking about something else, you're browsing the website while listening to me, okay, come back for a minute and pay attention on this, right? Yeah, I know you're not a superhuman. Your mind is running everywhere. It's a lunchtime, you're thinking of food, obviously, right? Okay. Right, so the population of initial, this is a new population. How do I know this is a new population? Anyone? What says this is a new population? Can everybody come up with
Because
an
we have the initial population for that interval and the growth on the other side of the equal equation. So,
well, more than that, if you concentrate on this t, right?
oh, it's at t.
Yeah. So this is at t. So you say current t, right? Yeah. Because this one says the previous t. That is the early time, right? Yeah. So this is the previous t, and this is the current t. And so this is the growth multiplied by delta t means whatever the new change. So this is the change actually, right? So you can see the change is nothing but the growth multiplied by t. So what does this means actually? So remember that I was talking about delta p is the change over delta t is the time, right? So this is what basically say dt dp by dt, right? Okay. So I need only the change here, which is a change of population. I'm not consider this part. So how do I convert this a change in population? You simply multiply this part by delta t. Why? So the delta t to delta t cancel out. So this is what remaining. So the growth is actually the change of growth actually, and multiply by this value, which means uh, dp over dt and multiply by dt kind of a thing. So this cancel out. So you have the little change. This is delta p, right? This is a little change. So in this case, this one says a little change, right? So that's how you come up with this. That's what it's showing here. So this is the little change, right? Plus the previous value, give you the new value, right? So new value is equal to old value plus the change. So this is what we were talking about, putting in a different terms of math, okay? Don't get confused. So that's what it is. Right. So this one explain what is T is, what is this, and what is this means. So that means early time, current time, and early time we do not buy the delta T subtract from the current time. So the finite difference equation is a new population equals our population and the change in population. So again, the same thing I repeated from above to this, okay? Right. So, right. So let's move on to the next slide here. This is a real bit confusing if you are not paying attention so far. Again, this is the same thing that I just explained on this slide, written in a different way. So, so here, I shuffled the equation. So what did I do here is, so what I came up with this equation. So I wrote this, these terms, okay, and this one we said growth, all right, and the growth is given by what? This one, right? dp over dt. This is what the growth is, right? Or on the other way of writing this is change in population over change in time. So this part I did not write on this slide. I think I should have write that. Okay, if you're not, mark it down. The growth is equal to dp over dt, right? And so I just need only the dp part here, change in population. So how do I convert growth to this? Is you multiply this one by delta t, and then you obviously have to multiply this part by delta t. This cancel out. The change in population is growth multiplied by the population. So I'm using that equation here. Okay. So this is what it says. Growth is equal to change in population over change in time. Okay. So that's what it says, right? And I'm applying this growth part to this. Okay. So how do I do that? Well, this is instead of I'm writing delta p is equal to delta t multiplied by growth. So I know already that. Is that clear? Did everybody understand this one? Yeah?
Yeah.
Okay, good. So, so instead of delta p, now I just say this one. So I can write my equation as new population is equal to old population plus, instead of a change of this, I write growth multiplied by delta t. Right, and then I'm writing this the other way. So unfortunately, I forgot to put a bracket here. It has to have a bracket. So this whole thing divided by delta t. So I'm putting growth in one side and put the rest in the other side. How do I do that? So new population means this right here, and the old population is this right here. Right, so this is old, this is new. Okay, so what I do is I subtract the all population from both sides. So subtract all population. Subtract all population. Both sides, right? Why? To keep this equation balanced, you have to do the same operation to the both sides. So then I will have a new population minus old population is equal to growth multiplied by delta t. Why? Well, this to this cancel out. This remains the same. So that means what? Let me write it putting growth in this side. So if I divide the both sides by delta t, again here, delta t, right? This delta t to delta t cancel out, this remains. So this means the growth, again, you can write it in a different way, which is a new population, right? Minus old population divided by delta t, right? So this is a new way of showing t, right? T, dp by dt is also equal to new minus old divided by change in time. Okay, so that is a new equation you can come up with. So that means dp by dt you can also illustrate by this. So that's what I came up with at the end. Right? So dp by dt is equal to new population minus the old population over time change. Okay? So yeah, is that clear? Yeah? Right. So if that clear, so let's move on. Why is that important to use this? Well, that is what the Vensim comes into play. So you give these equations, especially this equation to Vensim, and you draw this diagram. So this is a starting point, and this is the rate of change, and this is the population, right? And each time the population calls the multiplication of the growth rate to give the new growth, right? So what this means is my equation actually. This is how you showing my equation. My equation is this is a new population all the time. New population, right? And I said the new population on the previous equation that we said that is equal to RP, which is the current population, right? Which is the initial population. So you apply that and then you multiply by rate will give you the dp by dt, right? So actually, yeah, so this is not this new, this is not new population, this is actually a dp by dt, right? Is given by the initial population multiplied by the rate, which is giving you this value. And by using this value, you can fill the new population. So each time this one will change, and whenever it's changed, these values will change. And so this will, the whole thing will go on and on and on, because each time this value changes, right? If you have 100 people start, as I said, after 1 hour, you have 110. Right, so the next time when you come, you have 10 over 100 multiplied by 110. So this is the value after 2 hours, right? So this is after 1 hour, you have this. After 2 hours, you have this. After 3 hours, of course, whatever the value I get here, which is 0 to 0 cancel out, right? This to this cancel out, so this is 11 plus 100. So you have 111 after 2 hours, right? And then the next hour, 3 hours later, again you have a growth rate of this multiplied by 111 in this case. So like that, so it's growing. It's always depending on this value, which is a new population, multiplied by the rate, which is 10 over 100, will give you the new population rate. So when you calculate this, obviously you can find the new population, right? So on, it will go on like that. And so this is what the diagram says. It's going on and on and on. Each hour, when you calculate it, you can see this rate, and whatever the value will be the new population. So to illustrate this equation into this diagram right here is something that you have to understand. So this is very important point on any of the projects you do. I will go through each and every model I introduce about the diagram, okay? So these diagrams are the things that you play around and learn by yourself. So I will give you homework related to this. You will play around with it, and then you will get the idea, okay? Right, so once you've done this part right here, once you've done this part, this is nothing but the equation I was talking about. Again, if you missed what I'm saying, this is the equation. dp equal t is equal to rp. How do you draw this in this diagram? You have initial value, whatever it is, 100 in this case, and this value I put it as a rate. This value I put it as a population. This value I put it as a rate, and I just set up in this equation, this whole equation in this form, right? That's what I did. Okay. It will be hard for you when you're looking at it the first time, but by the time being, by practice, you'll get it. Okay. So don't get frustrated right now if you did not understand it. Hang in there. You eventually gonna get this. Okay. Right, and once you have this and you apply these equations, there's a place that you can apply these, and then you run it for 20 hours in this case. It says 20 hours. I'm running this program for 20 hours and see how much the total bacterial population currently I have, right? So you can see the growth. It's an interesting growth like this, and after the time step of 20 hours, you will have this graph. So where you get this graph, how can I generate this? Well, the system or the Vensim PLE do it for you, right? So you don't have to worry about calculating for each hour. And like I just did here, the first hour is 110, the second hour 111, third hour 100 and something, like that. If I do it manually for 20 times, it takes time. But instead of that, you can calculate instantly and give the answer or get the answer here. So that's what you do there. Well, I will stop here and talk about algorithms next time. This is just an initial algorithm. These are the equations you feed to the system. So these are the things you have to give to the Vensim. And Vensim get this diagram to find the relation between those values, and how you calculate each values that you have to tell the Vensim. And once you ask that, he will give the answer. So that is how the system do it for you. That is what we're going to follow up. But in the next section, the analytical solution I want to show is how do I really going to calculate this dp by dt differently, in a different way. This is a little bit math. If you don't understand things, there are a few things that you won't understand in this case, unless you do math and calculus. That part I will ask you to remember or memorize. I like you to remember some few things here. Actually, this slide right here, memorize this slide. Unfortunately, yeah, for many people it will be easy. If you know math, if you are not good in math, you can memorize it. Okay. Right, so I'll stop here